video is to discuss the concept of limiting reactants, which is a practical application of stoichiometry. It involves the use of stoichiometry to determine which reactant is consumed first in a chemical reaction, as well as how much product can be created. Now, up to this point, we've always been assuming that the reactants are present in the exact mole ratio to be used up with each other perfectly. So, for example, if we go back to a very simple reaction, and we make sure that it's balanced. Okay, so this tells us that we would need 2 hydrogens and 1 oxygen and we would end up creating two water molecules. So as it's written, there's assuming that you have exactly the amount that's shown in the chemical reaction. However, if there are some hydrogen and some oxygen present, but they're not in the perfect stoichiometric ratio. So, for example, what if instead this is what we started with? We don't know anything about how much product we can make yet, because we just simply have a bunch of hydrogen and a bunch of oxygen, and you can tell that they might now know they're not present in the perfect stoichiometric ratio. So you can tell yourself, well, for every one of these we're going to need 2 of these. So this one would react with these 2, and this one would react with these 2, and then you'd have a problem because this one would need 2 more. So at this point in time, you can tell that what gets used up first. Well, it looks like the oxygen would get used up, and then there'd be some hydrogen, some oxygen left over. And you could ask yourself, well, how many water molecules could you make? Well, apparently, because this is, each of these makes 2 of those, so I'd get 4 water molecules. Well, there has to be an easier way of doing this than doing something visually here. And that's what we're going to talk about today. We're going to talk about using stoichiometry to find out the answers to these questions. Okay, so first of all, we're going to have an amount of 2 reactants. And this is a little bit like when you go, if you're cooking, when you make cookies, we tend to just go to the fridge and pull out exactly what we need. But what if instead you went to the cupboard and you pulled out everything you had of all the ingredients? So you pulled out every amount of flour that you had in your pantry, and all of the sugar, and all of the butter, and all of the eggs. And you basically decided that you were going to just make cookies until something ran out. It's kind of what happens in chemistry. So, just like we would know how much flour, how much sugar, how much butter, how many eggs we had from the refrigerator, in this case we're going to have the amount of the reactants. Okay? We're going to limit it to just 2, because that's the most common thing we see in chemistry. We see 2 reactants very commonly. Now we're going to have to use the steps that we learned for stoichiometry, the D2U-M2, but we're going to do it from one reactant to the other. So randomly, we're going to just pick one reactant and say, okay, based on this one reactant, how much of the other reactant would I need to use this thing? How much would I need? And then I'm going to compare the answer. This will tell me what is needed. To what is available. And that's the amount given here. And I'm simply going to determine based on that information which reaction gets used up first. Okay, and then usually limiting reactant problems have two parts. The first part asks you to do this, to determine which reactant gets used up first. The reactant we gets used up first is called the limiting. It's called the limiting reactant, whichever one gets used up. Okay, the other reactant is called the excess reactant. That one has some left over. So it's like if you decided that you would run out of eggs before you'd run out of anything else. Hey, then everything else that you had left in your kitchen that could be used to make cookies would be in excess. Hey, if you just started making cookies until the eggs were gone, you'd have some of all the other stuff left over. That's what we mean by excess. The second part of the problem is usually asking us how much of the product could be made. In other words, we say, hey, if you just made cookies until your eggs ran out, how many cookies would you end up creating? So that means we're going to find the amount of product, but it has to be based on the limiting reactant. Alright, so let's go ahead and let's take a look at this. Alright, so this is the piece of information you need. You will need a balanced chemical equation. Oops, sorry, there should be one. And if you look at the problem, we have aluminum and iron oxide are the reactants. We're told that we have a certain amount of aluminum and a certain amount of iron oxide. So we're going to figure out, okay, if we combine these two, which one would get used up, which one would be left over, and the second part of the problem will be how much, if we put these together, how much iron would be created. Okay, so the first part is we're going to do a D2U-M2 problem from one reactant to the other. Now I'm just going to randomly choose aluminum to start with. The reality is it does not matter which reactant you choose to begin the problem. You will still find the correct answer. So I'm going to do a D2U-M2 problem starting with 35 grams of aluminum and finding, okay, how much iron oxide is needed to go with 35 grams of aluminum. I'm going to compare my answer to this amount, which is actually what's available, 75 grams. Okay, so remember our first D is dividing by molar mass of aluminum, which is about 27. Now I am rounding a little bit since I don't have my periodic table handy. So 35 divided by 27 is about 1.2, about 1.3. Okay, remember my second D is the coefficient from the aluminum, which is 2. That's about 0.65. Now, in the U part, for a limiting reactant problem, you have to go from one reactant to the other reactant. So now I'm going to switch over here to Fe2O3. Okay, so now we're going to take the iron oxide. Now we're going to figure out, we're going to do the M part. And go to Fe2O3. That's our U part. So we're going to take the 0.65, and we're going to multiply it by the coefficient in front of the Fe2O3, which is 1. And we're going to need to take it times the molar mass of Fe2O3. So I'm going to have to find that real quick. So I need 2 Fe and 3 O's. This is about 16. And this is about, let me check my periodic table. Fe is about 56. Okay, so I'm going to put that in my calculator. So I have about 56 times 2 plus 3 times 16. Okay, 160. So I'm going to take 0.65 times 160. And this is 104 grams of Fe2O3 needed. Okay, so the next step is I have to compare the amount of iron oxide that I would need for the 35 grams of aluminum to what I have. Okay, I only have 75 grams available. Okay, so it's pretty apparent that if this is what I need, this is what I have. I don't have enough. So that means that the Fe2O3 is limiting. That means that the aluminum is actually in excess. Okay, so what that literally means is if I put this much aluminum and this much iron oxide together and I let them react, all of the aluminum oxide would disappear because it's limiting, and there would be a certain amount of aluminum left over. That's what it means. So this is limiting, and this is an excess based on these amounts. If I had different amounts, that might be different limiting reactant. Okay, the second part of the problem says how much iron Fe could I make? Okay, a limiting reactant problem requires, once you've found the limiting reactant, you must start with the limiting reactant to finish the second part of the problem. Okay, so I'm going to do a D2U-M2 problem. Now I'm going to go with 75 grams of iron oxide, and I'm going to figure out how much Fe could I make. So I'm going to start with 75 grams of Fe2O3. I'm going to divide by molar mass, which I found over here, 160 grams. I already found it. You don't have to show the work twice in the same problem. Okay, so that is about, that's 0.469 grams, sorry, 0.469 moles. Okay, and it's 1 Fe2O3, So that's divided by 1. 0.469. Now I'm going to do the U part, which is I'm going to go to FE. So the 0.469 times, there's a 2 in front of the FE, .938, and I'm going to take 0.938 times the molar mass of Fe, which is right here, 56. Again, I've rounded a little bit from the periodic table. 52.5 grams of Fe can be made. Now remember, you have to do significant figures, and you have 2 sig figs. So that's 53 grams of Fe. Okay, once you have the limiting reactant, you can do all kinds of different problems. Okay, I'm going to show you one more example problem, and this will be finding the limiting reactant. We're going to use the same problem, but now I'm going to ask a different question. And that question is going to be, how much of the aluminum, the excess reactant, is going to be left over after the reactant? We said that that's what limiting reactant means. It means that the iron oxide is going to all disappear and there's going to be some aluminum left over. My question is going to be, well, how much aluminum is going to be left over? Okay, so this is another D2U-M2 problem. I'm going to start with the limiting reactant again. Okay. And now I'm going to work something that's going to be the exact opposite of what I did here. Now the reality is that sometimes, in this case I picked randomly aluminum. Aluminum turned out to be excess. You might pick iron oxide to have started the problem, and you would end up finding out exactly how much aluminum would be needed. So sometimes you're going to get a shortcut version of the problem, and sometimes you're not. It's just the luck of the draw. Okay, so I'm going to start with my 75 grams of aluminum again. Okay, and I'm just going to copy my work from above because I already did this part. I divide it by 160. That's 0.469 over 1 equals 0.469. The difference is now I'm going to the aluminum. I'm going to figure out how much aluminum I need. Okay, I'm going to take the 0.469 times, go back to the problem here. Okay, there's a 2 in front of the AL. Times 2. It's 0.938. And now I'm going to take that times the molar mass of aluminum, which is about 27. That's 25 grams. This is how much is used up. Well, from the problem I started with 35, so I subtracted 25, so 10 grams left over. Okay, doing the math you should be used to by now. The only real trick to these, if you have to think of very carefully, what do I start with? What is the amount that I begin the problem with? And when I go to the move it under, what am I supposed to be finding out? what amount of something am I supposed to be trying to determine? That's the only real trick to these problems, is you have to read the problem carefully and think logically about where am I starting and what is it that I'm trying to find, so that you put the right numbers into the steps for the D2U M2 problem.